Hello and welcome to a new video. This video is a Christmas special and it's actually my first Christmas special. And since Christmas is a special time, I thought I'd show you something special. And underneath here is something that I found in my basement. I purchased it a long time ago. Yeah, and I thought it would be interesting for you to see it. Maybe it is something new for you, which you have not seen before. Yeah, so I will show it to you right now. So let's have a look. And it's actually this here. It looks like a tube. But is it actually a tube, or is it a special tube, or what is it actually? So let's zoom in a bit. And if I turn on the light so you can see it a bit better. So you can see it looks like a tube with lots of tiny filaments in it. You can see them here. Maybe it looks like a bit like a Christmas tree, so it's perfect for a Christmas special. It is called the Osram EW12. It's actually a so-called iron hydrogen resistor. And this means that we have a thin iron wire inside here, and the glass is filled with hydrogen. And yeah, so this is it, and what it does is it stabilizes current. So in a specific range it is actually a current source. In a specific operating voltage range it's actually acting like a current source. So let me explain how this current regulation works. The wire inside, the iron wire inside, has a positive temperature coefficient, which means that if the temperature is low, the resistance of the wire is also low, and if the temperature is high, then it has a high resistance. So if a current flows through the wire and the current starts increasing, then the temperature of the wire also starts increasing. And when the temperature of the wire increases, then the resistance of the wire also increases, and therefore the current then decreases again. So that's the way how it is regulating the current. And if the current of the load decreases, then the temperature of the wire also decreases, and if the temperature of the wire decreases, then the resistance decreases, and therefore the current increases again. So that's the way how it regulates. And basically the hydrogen gas inside protects the wire against oxidation, and secondly it also enhances its regulation effect. And this regulation works in a specific range, and this regulation range is actually written here on the tube. It has actually two connections, so it's a 2-in-1 tube, so it has two ranges. Basically the first range is 35 to 105 volts, and in this range it regulates to 0.2 amps. And the second range is 80 to 240 volts, and in this range it regulates also to 0.2 amps. A short additional note is that according to the datasheet of this particular model, the maximum of the ranges should only be applied for a short time. The maximum permanent operating voltages are 85 volts for the 35 to 105 volt range and 200 volts for the 80 to 240 volt range. And yeah, these are the two ranges, and if you connect it to the 80 to 240 volt range, and if you operate it lower than 80 volts, it won't work properly, it won't regulate the current properly. And if you operate it at a higher voltage, then of course you can destroy it, which you should not do. And I've also prepared a setup right here, which we will use to measure the characteristic of this tube, so to check if it is still working properly after a long time, because this thing is from the 1930s. I found a data sheet of it, which is from 1938 actually. So let's see if it still works. I show you the data sheet before I start with the experiment. So here, let me put it aside first. So here we have the data sheet of the tube. It's in German, and here it says Osram Eisen Wasserstoff Widerstände, Osram Iron Hydrogen Resistor in English. And this is the tube that I have. It's the EW12. Here we have it, EW12. I think EW stands for iron hydrogen, or in German Eisen Wasserstoff, which means iron hydrogen, and 12. And here you can see, as I told you before, it has two ranges. The first range is 35 to 105 volts, and the second range is 80 to 240 volts. I will use the upper range for my experiment. And yeah, if we go here you can see how the EW12 can be connected. So if you connect it between pin number 5 and 8, it will operate at 80 to 240 volts, and if you connect it between 7 and 8, it will operate at 35 to 105 volts, and I will use again a 5 to 8, so the 80 to 240 volts. So before I start with the experiment, I will show you the circuit on my computer, and yeah, let's go. So here we are in LT Spice. This is the test circuit. It's extremely simple. Here I have a voltage source which is adjustable. I will show you how I build this voltage source in a minute or so. So it's adjustable from 0 to 240 volts DC, and it produces the voltage which I call U0. Then we have the current I0, which is the current which the iron hydrogen resistor will regulate. So it should be then about 0.2 amps. This current source here is actually the iron hydrogen resistor. And here we have a load resistor which is 150 ohms. And to test its current regulation ability, I will change this voltage here, and I will see if the current actually changes or not. So it should not change in the specified regulation range. And you can also simulate this thing just to show what the optimal current source would do. If I measure the current over voltage, so I've set it up that in a way that on this axis I will see the voltages which I sweep from the voltage source, and on this axis I will see the current, and this would be the optimum, this would be the perfect behavior of a current source in this case, which is first of all the current ramps up if I start increasing the voltage until it reaches the point where the voltage is high enough so that the current which the current source should regulate is reached. In our case 200 milliamps can flow. Because we have a resistor here, we need a specific voltage until we until the current can flow, of course, because of the Ohm's law. So if I probe the voltage on the resistor right here, you can see on this resistor I need 30 volts to reach the current. So first of all it has to ramp up that way, and after that it stays constant. If I increase the voltage more and more, it will stay constant because it's regulating the current, right? So the current through the resistor will stay constant from there on, and also the voltage on the resistor will stay constant. And if I measure the voltage on the iron hydrogen resistor, or on my regulating thing, then you can see the voltage here, let's zoom in a bit, as soon as it reaches the point where the current is possible, the voltage on the regulator starts to increase because it has to take the voltage difference between the source, which sweeps up like this, and the voltage which should be on this resistor. So you can see it should go that way. So this is how it should work, and now I will show you how it actually works. So here I have my setup, and yeah, first of all I will connect the resistor, the iron hydrogen resistor, to my circuit, and in this case I have to use these two pins right here because we have looked it up in the manual, in the data sheet. So I will do that. Of course everything is turned off, which is super important. Okay, you can see the resistor now, and now I show you the test circuit. Basically the only thing we need is the device under test, so the iron hydrogen resistor, and it is connected in series to the load resistor, which was R2 in our diagram which I showed you before. Here, this is my load resistor, it has 150 ohms, and I've also this fan, I've hooked up this fan to the resistor because it's getting quite hot over time. So here's this small little fan which is there for cooling it. Yeah, I will turn on the fan right now because I have to. Okay, I will turn it off and will turn it on later because it makes a distracting noise. So this part of the circuit is actually there for rectifying a AC voltage, because I actually have a DC voltage power supply which goes up to a high voltage, I think 350 or 400 volts, but it can only deliver 200 milliamps, and therefore I cannot use it for this circuit, so I have to use something else. So I actually use this this variable isolation transformer to supply the circuit with power, because it can deliver up to 3.5 amps and 0 to 250 volts AC. So this is much more than I need for this circuit. So this is my power source, but since it is AC I have to rectify it first because I need a DC voltage. And now back to the circuit, and here again you can see my rectifier. Here is a full bridge rectifier made of 4 diodes. All of them are 1N4007 diodes, and then I have this big capacitor here which stabilizes the voltage, so it removes the ripple voltage, it makes it into a flat line. And here I have 2 resistors in series. They are 8.2K and they are in series and directly connected to the output of the capacitor, and this is just for safety reasons, to discharge the capacitor when I turn it off, because without these resistors the capacitor would hold a very dangerous high DC voltage, and so I have to connect them for safety reasons so that the capacitor gets discharged after I turn off my transformer, to make sure that no dangerous voltage is there after that. So, and let's first have a look at the multimeters. And the first multimeter, this one, shows you the voltage, this U0 voltage, this or V0 voltage from my source. So it's directly connected after this capacitor and connected to this voltage, to the total voltage of both components. Then here we have the current. We have only one current in this circuit, and here we have the voltage U2 or V2, which is actually the voltage on my load resistor. And what I expect is that after a certain voltage value here is reached, then the current won't go up anymore because it's then stabilizing the current, and also the voltage right here won't go up anymore because it's a resistive load, and if the current is constant then the voltage is also constant. I will set this to a fixed range, to the 400 milliamps range, because we're expecting 200 milliamps, so that it does not change ranges while the experiment is running. Here this is set to 40 volt range, which is fine because we're expecting 30 volts, and this thing is also, I think, in a high enough range so that it won't auto range. Okay, so let's start with the experiment, and I turn on the transformer now, and we have 11 volts DC on the input, we have 38 milliamps and 5 volts on the load resistor. So now the regulation isn't working because the voltage is too low on the input. So I will start increasing the voltage slowly, and let's see, a beautiful thing will happen shortly. The regulation will kick in. I increase it. One important note also is, since this works with temperature, it needs a bit of time until it heats up, and therefore until it works fine. You can see it already starting a bit because the current is decreasing over time, and this is because the thing is heating up and starting to work. But now the voltage is still too low for it to operate correctly, because again I've connected it on the 80 to 240 volt input, so we have to increase it more. Okay, now we have 162 volts on the input, and it also starts to glow a little bit, but it has disappeared now, so it won't look like a Christmas tree, unfortunately. Sorry for that, but I can't do nothing about it. And if you look at the current here, you can see the current starts decreasing a bit because of the thing heating up, and if it gets hot, the current decreases, as we know. And yeah, and you can see the regulation now actually works, because the current should be 0.2 amps, and it is about 0.2 amps. This is not a high precision thing, of course. And now I will show you. Now we have 0.21 amps at 160 volts input, and here 31.5 volts on the load. And if I now, let's say I increase the voltage now to 200 volts, so you can see the current does not change much. The current is still on 0.213 volts, and the regulation still is doing its thing a bit because the current goes down, so it's absolutely perfectly fine regulating. And of course the voltage on the load also stays the same because the current stays the same, and it's a resistive load. I should turn on the fan now, the fan right here, because the resistor is starting to get hot, the load resistor, so that nothing starts burning. And as you can see, it's working better than expected actually, because it's quite near on the current which it should have. Is 0.209 amps, and it should have 0.2, so it's very close. So I will increase the voltage even more. Let's increase it to 230, and the regulation still works. Now it's on 0.211 amp, which is very good. It's working very well actually. I'm impressed. Don't forget that this thing is from the 30s, so it's quite old, and it's still working very good, very fine. I will now decrease the voltage, let's say so, to 130 volts. And now you can see the current now starts to ramp up again, because the thing is cooling down, and therefore the regulation still kicks in. And after a while it settles. But actually it's extremely good. And now after a while it has reached its current again, so now we are almost at 0.2 amps again. So it's working very well. It is getting hot a little bit. So I will decrease the voltage even more, and after a specific voltage it will stop its regulating action. Now at 115 volts input it's still working. But I think if we go even down even more, so now we are at 90 volts on the input, about 90 volts. Yeah, and now the regulation does not work so good anymore. So now we have 0.79 amps. It's going up again, but now it's not working so well. So if I decrease the voltage even more, yeah, of course, now the regulation isn't working anymore again. So, but it works pretty well. I will put it again in the range in where it is happy. So let's put it, let's say, to 200 volts again. And you can see the regulation is working perfectly fine. It's absolutely amazing and astonishing what this old technology still can do. It's absolutely amazing. So I think it's a perfect thing to show you this very special, amazing stuff in a Christmas special. And I'm so amazed by this thing that I had to plot a diagram of it, how good it works, and I will show you the diagram. I've done it with Microsoft Excel, just a quick diagram. Just measured some samples of these three values which we have here, and I've put it into a diagram, and I will show it to you right now. So for this I will turn off the high voltage first, then the fan. Okay, and back to the computer. So here you can see the results on my computer. Here we have the circuit again, and let me zoom in a bit on this. There we go. And so here on the, so here I have U0 or V0 in volts. So there's a voltage directly on the input, which is across both devices, across the current source or the iron hydrogen resistor, and across the load resistor R2. R2 is 150 ohms in this measurement. Then we have I0, which is the current flowing through both devices. Then we have U2, the voltage on the load resistor, and U1, the voltage on the current source resistor, on the iron hydrogen resistor. And I calculate U1 because it's just the difference between U0 and U2. So it's just an Excel calculation. We have B4, which is U0 minus D4, which is U2, and then I get the voltage on the current source. So and here you can see that after a specific input voltage, the current as well as the voltage on the load stays fairly constant. And if I scroll down, here we have two diagrams. The second one is the voltage on the load resistor. The first one is the current. And here you can see on this axis right here, we have the voltage, the input voltage, U0, and here we have the current, I0, and after a specific input voltage, after about 100 volts, 100 or 110 or so, it starts stabilizing. So here you can see this is the startup, and here it starts stabilizing, and you can see that the current is fairly constant. So if you compare this with our simulation in LT Spice, here we have the perfect behavior, and back to the diagram what we have actually measured. And what's also important to note is, for measuring this, I have I turned it on quite some minutes, because I want to make sure that it is already hot, so that it's working as it should, because if it's cold it's not working fine. So I've started it up for some time with 240 volts on the input until it has got hot, and then I measured actually the diagram in reverse. So I started with this sample and then I measured the samples in this direction. Okay, and I also waited between the samples a little bit for it to adjust to the current. Okay, so this concludes my Christmas special about this amazing iron hydrogen resistor. I hope you had as much fun watching it as I had making this video. So I can say thanks for watching and have a happy Christmas time. Bye.